All right, recording is started. So thank you. Welcome to Wednesday. I know last couple of days we been doing some unit one review, like kinematic motion. And so I think what we're going to do for between now and the AP exam is something like this. Is we'll do a little bit of review for each section. Next week, I'm going to have you guys do the multiple choice half of a past AP exam, and then we'll go over the answers. I think probably like all the next week. But then my honors classes, they're off studying more about physics. So right now we're doing electromagnetic spectrum and optics. We're going to do theory of relativity. There's going to be thermodynamics, electricity, quantum mechanics, a bunch of stuff that you guys aren't actually technically tested on. And I'd like for you guys to know about this, all these topics too. Especially a lot of you guys, this might be possibly the only physics class you're going to have, or the last one for a long time. Oh, yeah.
Are we going to be tested on these things in this class?
No, I'm not going to test you guys on this stuff. But I do want to give you guys like a crash course on some of the stuff, so that you're at least familiar with it. You've seen some of the main demos, just paint with the broad brush, give you guys a big picture of some of these ideas. And then if you're really curious about anything, or you want to look more into it, at least you'll know the concepts that these certain ideas exist. And so the plan is to today and tomorrow give you guys a crash course on this. Now this is my honors classes. I'm taking 2 weeks to do this stuff, and I'm going to try to get this down to 2 days for you guys. So see what I can do. Friday's gonna be flex day. If I need to show you guys more demos, then I will. We'll see. Okay, so let's flip the screen over. Let's see, share screen to. Okay, I'm gonna work up to that right there. But we start with so electromagnetic spectrum. Now this is electromagnetic spectrum. EM waves are oscillating. We're looking at oscillating electric and magnetic fields. Now all these waves travel at the speed of light. Actually, the speed of light refers to speed of all electromagnetic waves, but really the speed of anything that's massless. Anything that's massless has to move through space at 3 × 10⁸ meters per second. But you have these different wavelengths and frequencies. Now you guys know longer wavelength is lower frequency and vice versa. So there's a very tiny part of the EM spectrum that our eyes can detect and interpret, and that's what we call visible light. Right? All the colors of the rainbow. So we're RGBF, right? If you go too high wavelength, you get to infrared, and your eyes can't see it anymore. Although there are some animals whose eyes can detect infrared and interpret that. And then microwaves, and then eventually radio waves. Okay. Radio waves is usually like anything about a meter or longer. Okay. On the other end, if you go to violet and then get too high frequency, that goes into ultraviolet, and again, your brain can't interpret that well. Your eyes can't take that. Again, some animals can. That's why some flowers or butterfly patterns you can only see if you're under UV light and interpret that back to visible. Right, then X-ray and gamma ray. So there you go. So I'll travel at the speed of light. Okay. Flip my screen over. Okay. So trying something a bit different here. I mean, usually don't teach this way, but gonna do my best. So yeah, sorry, why did not put that? Way I'm gonna do this is I'm actually gonna go through Paul Hewitt's textbook and just use this as a checklist, tell you guys a little bit about each section. Again, I'm trying to get this down to 2 days worth of stuff. Okay, and then I have some other demos and some other work we've done in my other classes that I can use to supplement too. Okay, so we got light. Oh, there's this fun history story. Go back to the 17th century. There was this Danish astronomer, Olaus Rover, who made the first calculation for the speed of light. So he was using this method of as Earth goes around the sun. He was looking at it through a telescope at Jupiter and one of its moons, Io, that was revolving around Jupiter. And he noticed as Earth was moving towards Jupiter, that Io's time period of revolution got faster by about 13 seconds. And as Earth was headed sort of away from Jupiter, that time period increased, got slower by 13 seconds. Now, it's not because it was actually changing its motion, but it's because the fact that this distance was closing and then getting further away, that the information was at different rates. So Now this was like I think 42 or 43 hour revolution, changing by plus or well, minus or plus 13 seconds. He realized that if you knew this distance and you knew that time difference, you could calculate the speed of light. Now this is one of those problems you have to sit down and think really hard on. So I won't do it with you guys, but just tell you that the story does exist. If you want to look into it. He got 2.2 times 10 to the 8 meters per second, which is actually pretty close to 3 times 10 to the 8 meters per second. Did I do the exercise with the guys with the tooth wheel calculating the speed of light? Did we do that? No. Okay, so that one I probably will do with you guys. There was another experiment in 1849 that actually got it like pretty accurate to 3 times 10 to the 8 meters per second. Right. Okay, waves we talked about. I'm gonna skip some of these things. Okay. Okay, polarization. Do a quick demo with you guys. So the fact that light can be polar. Zoom out so you can see my book. Polarization. The fact that light can be polarized is evidence that it is a transverse wave, because transverse waves you can polarize. Right? Longitudinal, it wouldn't make any difference, right? So here's a couple of polarizing filters. It's horizontal gets through, horizontal, vertical, it's black. Okay. So 3D glasses. So what if you had, say, how do you get, say, 2 different images to your brain that you're, one for each eye that your brain can put back together and get some kind of like 3D perspective, right? Because how do you see in 3D? Well, the fact that you have 2 eyes, they each get a little bit different image, right? So if you could send those different information to each eye, you get 3D. Now, an old way of doing it was to have, say, a red image and a blue image, right? You put on these glasses, one red, one blue, and then you get a little bit different information from each one. The newer way uses polarization. So it's more like this. Like if you have one, say this on your left eye and this is on your right eye, right? And then you can get a different polarized image to go through each one, something like that. It's actually a little bit more technical than that. There's like a spiral polarization. That's sort of the principle behind how 3D movies work. Okay. Color. All right, so you guys know that each color is a different wavelength and frequency of light. Long wavelength closer to red, shorter closer to violet. Now, talk about color mixing. So what are the let's say I wanted you guys to paint the picture, but I'm only going to give you guys a small number of colors, let's say 4 or 5 colors. Okay? But you want to have like all the colors if you could. Okay? What are some good colors to choose for painting a picture, like pigments? Probably like primary colors. Now you might say red, yellow, blue, and that would be okay, but there's technically a better answer, which is it's sort of like red, yellow, blue, but I'm going to call it magenta, yellow, and cyan. Okay? These are actually the colors in your printer. So these colors mixed by what's called subtractive color mixing. So anything that's like pigment, colors in a printer, paints, they'll absorb all the colors from the world except for the wavelength you see, and then that's reflected back into the world. But then once you start mixing more colors, like if you mix all your paints together, you don't get like a really dark, muddy brown color because it's just subtracting more and more light. So less is reflected back into the world. Okay. Here's them mixed all together. This is just the colors. This is plus black ink, but they look nearly identical anyway. Okay, okay, so here's like how pigments work. But what about if you look really close at your phone screen? If you get really, really close and look on your phone screen, there are only 3 colored bulbs that show up on your phone screen, and it's not these 3 colors. It's not magenta, yellow, cyan. What are the 3 colors on your phone screen?
Red, green, blue.
Red, green, blue. Yeah, it's called RGB standard. Actually, I have to flip back a few pages for that. RGB standard. Okay. So actually, I do want to flip my screen and show you guys an image of this. Okay. There's also a Paul Hewitt video where he stands in front of 3 different colored lamps that are up right here. Just like Warner said, red, green, blue, RGB standard. Okay? And you notice that, well, here, the color mixing, if you mix all the colors together, you get white light. Ooh, that's like the opposite of mixing a bunch of paints. It's darker. Now here's getting brighter. Okay? So Isaac Newton was the first person to figure this out, by the way. He was using a prism and realized that white light, you could break apart different colors because each color would refract a little bit different angle. That's what this one is right here. Right? Each color, of which you talked about refraction. So each wavelength refracts a little bit differently. Okay? And then if you put all the colors back together, you get white light. Notice something like yellow, which you might normally think like a primary color if you're talking about subtractive color mixing, is actually like the average of red and green wavelengths. If you mix those together, this is a additive color mixing. Put them all together, you get white. Take them all away. That's how you get black. Okay. Stop share. Right, let's go to, oh, let's do this exercise real fast since it's here in the book and this is fun. Okay. So stare at the middle of that image for about 30 seconds and I'll tell you what this is about, what's going on. Hey, see this. This is called retinal fatigue. Now, your eye has different cones in it. You should have 3 different cones. You should have a red cone, a blue cone, and a green cone, or at least that's the wavelengths that each one would pick up. And from that, you can see all the ways you can see. Okay. Now, you guys are like fatiguing the colors that those correspond to on the screen, so that what I'm about to do is flash a white screen for it, and you should see the opposite, right? The opposite of those wavelengths. This is kind of like if you walk into a bakery, you smell bread, but if you hang out for an hour, like your senses get dull to that. Okay, so you guys ready? You guys see like an actual American flag kind of hovering right there? Okay, it's pretty cool, right? Okay, so check some of those. Zoom back out. White sky is blue. Okay. Honestly, this one I've never 100% understood myself, but it's something involved Rayleigh scattering, which actually doesn't have the term here for that. I don't think it's called Rayleigh scattering. Has something to do with the like longer wavelengths tend to are able to pass through, say like a atmosphere full of molecules, but shorter wavelengths get scattered, and so if it's like a sunset where all those long wavelengths are getting through, you perceive like more of the colors, like all the reds that actually get through. But if you're like looking at another part of the sky, then you see the color scattered, which are the shorter wavelengths, which is more like blue color. So I know that's not a very good explanation, but that's normally goes something like that. Okay. Ooh, line spectra. Okay, so suppose you're an astronomer one day and you're looking at some distant planet and you're trying to figure out, I wonder what its atmosphere is made of. Or maybe you read a science article and says like, oh, we found an Earth-like planet. We know this because it has water on it. Well, how would they even know that some distant planet would have water on it, right? Or possibly does? Okay. Well, because you can get information about what's in its atmosphere by these line spectra. So each atom will, if you shine light on it, will emit certain wavelengths of light back and forth because of the structure of the atom, like at the atomic scale, how the electrons are arranged a little bit, right? So this top one refers to hydrogen, this middle one is sodium, this bottom one is mercury, but each element has its own like fingerprint, right? So yeah, so if you see some distant light enters this tool that's called a spectroscope. Of course, they'd all be laid on each other. Then you can take them apart and say, I see that there's some hydrogen, there's some oxygen, maybe it's in a 2-to-1 ratio. Ooh, that looks like there's probably a bunch of water, say, in that atmosphere, something like that. So spectroscope, line spectra. Now, here's where I make my own little side story. You guys know what red shifting and blue shifting is? Okay. Tell you guys the story because it's going to link back to this. I bet some of you guys know what I'm talking about, and some maybe not. So here we go. So I'm going to draw a bunch of galaxies. Okay. Bunch of galaxies in the universe. Okay. By the way, people only knew the existence of other galaxies only in about the last 100 years or so. Okay. So a bunch of galaxies spread around the universe. I'll call this one the Milky Way. Okay. And when astronomers look at other galaxies, Edwin Hubble was the first person to figure out what I'm about to tell you, is that the light coming off all these other galaxies was a little bit red shifted. Everything was a little bit red, or let's say you use the spectroscope and we're getting these line spectra, they'd be shifted a little bit to the left of what they would be, say, in a laboratory. Now, why would that be? Can you guys guess why everything would be shifted a little bit to the left? Why everything would be red shifted a little bit? It has to do with this poster right here, the Doppler shift. Right? You guys know if a car is moving relative to you, it's headed towards you and then away from you, it sounds like, that's like Doppler shift, right? okay, so if something's in motion, it involves waves, you'll get frequency changes. Oh, light is a wave, light's a transverse wave. Huh, so if you had some kind of shift, maybe like a decrease in frequency, hey, that might be evidence that something was moving away from you, kind of like that car. And Hubble figured this out and realized that, oh, actually all these galaxies are moving away from us. It was a mystery before Hubble. Why, if you have, for a long time, it was assumed that maybe the universe was like a stagnant size because they had nothing else to go on. So that was just a starting assumption. But that would be kind of weird because if there's universal gravitation, everything should just like crunch together, right? So Hubble realized everything's redshifted, everything's moving away from us. But you know what? Furthermore, the further away galaxies are, the more the redshifting is. And this is related to something called cosmological principle. Okay. Cosmological principle tells something about how the universe expands. It expands in a way that's not super intuitive. One thing cosmological principle says is that there is no such thing as the center of the universe. Or another way you could think is you could say the center of the universe is sort of like everywhere. Now, if you have a classic explosion, let's say take a grenade, throw it on the ground, walk away, explodes, there is a center of that explosion, right? Well, the Big Bang not really work like that. By the way, some evidence for the Big Bang, there's background radiation. If you're like tuning in your on your radio, car radio, say you're between stations, hear some static, like a psh, right? Supposedly, what I read is that about 10% of that static is attributable to background radiation, like from the Big Bang itself, and also just the fact of universal expansion itself, right? If you rewind the clock, then it's about 14 billion years back, everything would have converged together. Right? So how does this Big Bang work, and how does universal expansion work? Oh, yeah, Alex.
How did they know that there wasn't something here before the Big Bang and it was just pushed out because of the Big Bang?
Well, that is a mystery. Nobody knows what happened before the Big Bang. And eventually tell you guys a bit about relativity too. So even time, time is part of the fabric of the universe too. So like time doesn't really exist outside of the universe. It's just like a dimension itself. Yeah, that's that's one of the biggest unanswered questions. Like all the universe, right? It's like what's outside the universe, what was before the universe. Those are unknowns. So there is actually a, all right, so if this is true, if there's no center of the universe, or you could, here's the other way to think of this, you could be standing on any one of these galaxies and everything's expanding away from you. Sometimes this cosmological principle, I've seen this analogy of, think if you take 3 spatial dimensions of the universe, you know, there's more than that, there's also time and possibly other dimensions that we can't perceive too. I mean, that's possible. Maybe we just don't have the tools to understand other dimensions, but we know 3 spatial dimensions. I'm going to take those and put them on the surface of a balloon, right? So a 2D latex surface, okay? And I'm going to redraw these galaxies all over the place. And now, as you blow up the balloon, don't these galaxies move away from each other? They do, but which one is the center? Is that the center galaxy? Is that the center galaxy? Well, there's no galaxy that is the center galaxy. There's no such thing, right? They'll just kind of expand away from each other. All right, well, the universe is kind of like that too. Now, you really have to wrap your mind around that because it's not like a conventional explosion. And that sets up an interesting consequence, which is that there is an observable limit to the universe. I'll call this the observable universe. Okay. Because if you get far away enough, let's say like there's a galaxy like right here, okay, if space is expanding faster and faster, there's some, the further away you are, the faster you're moving. And at some point, say like this dashed line right here, the space between 2 galaxies is actually expanding faster than the speed of light. So a galaxy would be moving away from us faster than light. Now, there's a rule that says you can't ever go the speed of light, or definitely not faster than it. But the catch is you can't move through space at that speed. But space can expand between, say, 2 galaxies faster than light. So there's only so far we can see. Actually, that's this photo right here. You guys see this one? That's called the Hubble Deep Field. Let me tell you guys a story of that while we pull this up on Google just for the video. Let's see. Share my screen. Something weird going on there. Hubble Deep Field. Right, so story here is about a couple decades back, the Hubble telescope was pointed at a random spot in the night sky. And we're talking about like grain of sand held at arm's length. That's the angular space it took up in the sky. So tiny, tiny pinpoint. They didn't know what they were going to get. It could have been just a black rectangle, but they got this image here. That is like the edge of the universe. That's as far as we can see. So are there galaxies beyond that? Almost for sure, but again, the light information will never reach us, so we'll never quite know for sure. Right, so go back over here. Okay. Oh, and then so just to one last point about this, if you know how much red shifting there is, you can calculate not only how fast is a galaxy moving away from you because of Doppler shift, right, but you can furthermore calculate like how far away it is. Right? Those two go hand in hand. Okay. Right, reflection and refraction. Right, so reflection, there's a law of reflection that just very simply says that the angle of incidence is equal to the angle of reflection. Now, the angles that reflection is measured at is with respect to this normal line. So this could be a mirror. Here's your flat plane mirror right here. Okay. And see this dashed line that's perpendicular to that? Okay. That's the reference line that angles are measured to. Same story for refraction when we eventually get to that. So whatever angle this is, however many degrees, this is the same angle. Okay, so that's real simple, right? What about the like curved mirrors? Ooh, I see like a curved mirror type going on here, right? Huh. Maybe if this guy is looking at like the backside of the spoon, I see a slight curved spoon. Huh, it looks kind of smaller here. Versus if he turns the spoon around and this would be like convex. Okay, now this guy's looking inside the concave portion, it kind of blows him up a little bit, right? Hey, maybe kind of like a cosmetic mirror. I have one of those here. Now this side is just a flat plane mirror, but if I turn this around, it's a cosmetic mirror. It has a slight concave curvature to it. And so if you hold your face close to it, then see a larger image. So bring this up too. Get towards that. What are different? Wait, does they talk about? Oh, so here are some ray diagrams in here. Well, I know I did some ray diagrams, so yeah, okay, we bring those up. There we go. Okay, so if you want to figure out what is an image going to look like, let's say in one of these funhouse mirrors or some kind of curved mirror, here's looking at the backside of a spoon. Now, backside of the spoon, there's only one thing that's ever going to happen. Right? You're going to see a reflection of yourself that's going to be right side up, and it's going to be smaller. And it's also going to be called a virtual image, which is to say like on the opposite side, or reflection looks like it's on the opposite side. Right, now, going from top to bottom, there's a really tight curve, then there's a shallower curve, and then something that's approximately a plane mirror. Okay? Now, the approximate plane, your image is going to appear to be, well, if it is a plane, you should be the same size and exactly equidistant on the other side, right? And since this is getting close to that, it's starting to approximate that. Now, how can you figure out where this is going to be? So you can do a ray diagram like these are, or there's an equation that goes with this too. So take you guys through this. Now, these are parabolic mirrors, meaning that this is like the shape of a parabola. You guys know a parabola would be like y equals x squared. We'll take that, turn to the side, flatten it out, some version of that. Okay. But could you take, say, a circle and like put it flush to this point right here? See, I have a ground, like a dashed ground, like as a reference line. If you take a circle and put it like flush here, okay, you could do that. You could blow up that circle bigger, bigger, bigger. But at some point, you make the circle too big, and it's gonna like separate from this point. So what's the biggest circle you could put that would be flush to that point? So I got like one dash outlined right here. Okay. Well, that circle would have some radial size. Okay. Now think about what that would mean, that radial distance. So I've got a couple of rays going through here. So one ray, see if they're like a billion rays all bouncing around the sky in all different directions, but you only need to follow a couple using this method to figure out where the reflection is going to be. So I'm going to have one ray going parallel to the ground, right? This method, parallel to the ground, and it's going to bounce off this surface. Now, if this is a flat surface, of course, it would bounce just straight back, but it's not. It's curved, so it should bounce kind of up to the left. But how could you quantify that? Well, this is where the law of reflection comes in. Right? A little twist on it. So here's that dashed line, the normal line that the angles are measured with respect to. If you extrapolate backwards, it should cross exactly through the radius, the center of this circle, right? That makes sense? Okay. And if that's true, then, and combine it with the law of reflection, this incident angle should be this angle of reflection of one. Then if you extrapolate that ray backward, it should go through a point that is, well, where this distance called the focal distance would be half of this radial distance. That's this formula right here. Focal length is equal to half the radial stuff, right? Like that. So this focal point is a really important point for measuring curvature. Actually, for the rest of these, I didn't even include the center of the circle. I just did a bunch of focal points, right? Okay. So this incident ray is going to bounce off so that you could extrapolate backwards and it should go through this focal point. Yes, sir. Now, of course, there's no light that's actually crossing the surface. This is a mirror, right? It's all on the left side. This is all that's really going on. But you can extrapolate backwards to figure out what the result's going to be. We go to the second picture because these first pictures are kind of the same, but the second picture is just a prettier one to look at. So the boing bounces off that way, extrapolate backwards through the focal point. Okay. Then take another ray, also from the top of his head, okay, and head straight for the focal point. And that one is going to bounce off the boing parallel to the ground again. Okay. But if you extrapolate backwards, there's two places where these rays cross. One is at the top of his head, because I've been doing everything from the top of this guy's head. But the other place is where the image is going to show up. Now you could do the same process for his feet, but his feet are going to just line up on this reference line. That's the ground, right, the ground line. It goes through the focal point anyway. So go ahead and put the image there, the feet of the image, right, and then that's what the reflection would look like. Again, closer to a plane mirror, it's going to be close to the same size. Awesome. Right. Now, what about if you turn the mirror around and make it concave? Right? Hey, kind of like that cosmetic mirror I was just showing you guys, right? Concave mirror. Right. So I got, I should have labeled this object. I got object, object, right. Object. Okay, so I got some black ink here. We got all the objects. Okay. Now, backside of the spoon, there's only one outcome that's ever going to happen. Okay. But concave, well, there's actually different scenarios. Okay. So if you're, I know you drew a stick figure here. This could represent your eyeball, right? What if your eyeball is inside the focal distance? The first picture is like that, but that's the only one that's like that, right? If your eyeball is inside the focal distance. So you do that ray diagram method that I showed you guys on the opposite page, and you'll get an image that's going to be virtual because it'll appear on the opposite side, but also be blown up, like bigger. Right? That's kind of the point of that cosmetic mirror. Right? But if you either use a less curved mirror or if you pull the mirror further away so that your eye is sitting right on top of the focal point, what's going to happen? Well, you'll get like a blur of light that's just going to result in no image. There'll be nothing discernible. You guys can try this too. I'll pass around something in a minute where you can try that. What if your eye is outside the focal length? Well, that's going to create what's called a real image. Hey, maybe like the image might be like hovering in front of the mirror. Now, this particular setup right here, this exact third picture, what you'd have to do is have like a screen here, maybe like a piece of paper, and then you'd have to view it. That's why I drew an eyeball right here, like looking this way. You can see it'll be an inverted image, and it's called real because it'll be hovering in front of the mirror. And if you back up to more than twice as far from the focal point, see, like here it's just barely outside the focal distance. What if it backs up to more than twice as far? Well, that would create a real image that was like it was just hovering in front of the mirror like that, which is exactly the explanation for this pig. You guys, probably most of you guys have seen this. If you haven't, then I'm going to pass this around. So there's an actual pig down here at the bottom. Okay, somebody threw a couple of tar pigs down here too. Okay, those on top. And if I turn this, see if I can get it to sort of work on screen. You can kind of see it. I should have got a video demo, maybe be able to play that. I'm going to pass this around. You guys give a good look at this. Also, you can break these apart and hold these closer to your face and further away to get each of these different scenarios. So I'll pass this around. Okay. But it's a really good illusion too. You know what I'm talking about. You see that on the screen. Let me dig up this demo real fast. Where's real image? So it looks like that. Looks like, hey, there's a pig there, right? But just try to pick it up. Just try. Not gonna happen because it's not really there. It's actually there it is. It's actually down there. It's barely on screen. Right, so that's how you can get that to work. So you need these parabolic mirrors or concave to get that illusion to work. Okay. Now, is there an equation that goes with this? Yeah, the equation goes like this. 1 over the focal length is equal to 1 over distance of the object from the lens plus 1 over distance of the image from the lens, something like that. And these numbers could be positive or negative. If one's negative compared to the other, that just means it's on the opposite side of the mirror. Let's say like a virtual image situation. Let's run a couple of calculations for these. I'll just do a couple on the side. Okay. So let's look at this one right here. Try this out. So 1 over the focal length. Okay. So here's the focal length right here. Right, remember, which is half the radial size of the circle that would fit flush to it. I'm getting 7 centimeters. That's 7 centimeters right there. So 1 over 7 centimeters equals 1 over distance to the object. Right now the object is over here at, okay, this is 6 centimeters away from the surface. Okay, this is all relative to the surface. 1 over 6 centimeters. Oh, one more thing too. These two numbers I just wrote, they're on opposite sides of the mirror, so somebody has to be negative. Usually the object is treated as a positive number, so I'm gonna slap a negative sign on this focal length. And then let's do some algebra and solve for where the image should be, because you see the answer with the ray diagram. This ray diagram and this equation should tell the same story. So I'm gonna take it's 1 over -7 minus 1 over 6, and then take the reciprocal. I'm getting, cut through some algebra steps, negative 3.23 centimeters. So about negative 3¼ centimeters from the surface. And let's see if it is. Okay, well, it's on the correct side. Okay, so it's about 3.2 centimeters. 3.5, yeah, 3.5 centimeters. Right, so it does help. Let's look at this one because this is approximately a plane, right? Hey, what if you did have a perfect plane mirror, like a flat mirror? Right? Where do you guys think the focal point would be for a perfect plane mirror? It looks like the flatter it's getting, if it's really tight, it's really close. And the flatter it's getting, see it's like moving out, moving out, moving out. If it was a perfect plane, you think you'd have a circle of infinite size that could fit flush to it? And so you think that the focal point would also be infinitely far away? So that would look something like this, 1 over infinity. And then where's my object? This is about, let's say about 4 point something, maybe like 4.3 centimeters, something like that. 1 over 4.3 centimeters. Okay. Plus 1 over distance image. See what we did before, like solve for this and see if the ray diagram tells the same story. Okay. Right, now, I'm gonna say probably most of you guys know this one. What is 1 over infinity? And it's not infinity, it's what? 0. Yeah, 0. Okay. Right, so just in case, okay. How about this? You go buy a lottery ticket and there's say like a 1 in 20 million chance that you'll win the big prize. 1 in 20 million. Ooh, now 20 million, it's a big number. Okay. 1 divided by 20 million. So for all practical purposes, your chances of winning the lottery are 0. Don't remember that. Especially if you've been through calculus, you would definitely, because that's an important concept of calculus, right? Okay, 4.3 centimeters plus 1 over di. Okay, now you could do the algebra, but I bet you guys can just look at this and see what the answer has to be. Doesn't this di have to, well, be a number that would cancel out this fraction? And the only thing that could be would be negative 4.3. Okay, so as long as you have a plane mirror, which is the math of what's going on here, your reflection should be the same distance from there, but on the opposite side, right? Let's see, is this written? And just eyeballing it, that looks pretty close to true, doesn't it? Let's get an exact measurement. I'm getting 4 centimeters, like 4.0. Well, there was a slight curve to this, has a finite focal point. So yeah, that looks pretty consistent, doesn't it? Okay. Okay, then it gets to refraction. Okay, so refraction is going to be like light bending, this sort of thing, right? So I got a prism here, shine light through, it's going to bend. Okay. Now, how much is it going to bend, and why does it bend? Okay. Well, light slows down inside material. So the whole light moves at 3 times 10 to the 8 meters per second. That's really only true in a vacuum. It's almost true through air because air has an index of refraction that's very close to 1. Index of refraction is how you can quantify how much light slows down, which eventually can lead to the explanation of why it bends. Okay. So, let's see if there's like a table of values in here somewhere. Some textbooks have one. Okay, we're not, but index, I'll go ahead and define it for you guys, and I think you can make something from here. Of refraction. I'll call it N for index of refraction. It's equal to the speed of light in a vacuum compared to the speed of light inside the material, right? Which is always going to be more than 1. So for air, I want to say it's like 1.001, I think. Right? So it's just a little bit bigger than 1. For perfect vacuum, it would be exactly equal to 1 because it's 1-1 ratio. For water, I think it's like 1.33, right? So it tells you like how much it slows down. So it slows down by about 33% through water. And this, we do have a lab that involves trying to calculate what the index of refraction. So I want to say it's like about 1.4, 1.5, something like that. It depends on the day and the measurements you get. But so why would light refract? Why would it bend when it slows down? This is the same idea of here, come with an example of refraction. If you throw a straw into water, the straw looks like it's all broken and it's all bent, but it's not really, it's just an illusion, right? So what's going on there? Right, so to do with here, this is a really good model right here. Really good model. Okay. So look at that. It's got light refracting the water. Okay. So say you have some incident ray that's drawn in orange right here, right? And all these black lines could represent wave fronts. So we have like crest. So each of these black lines represents like crest of a wave, that incident ray. Okay. All right. Well, when this light hits this water, okay, it's going to slow down by 33% for water because the index of refraction. Okay. Now, when it slows down, see how the these wave crests are still going to match up. Right? I mean, they have to, right? It's like crest here, crest water, but they match up at the same point. That means that the frequency of the wave fronts leaving the air is equal to the frequency of the wave fronts entering the water. I mean, that makes sense, right? Frequency matches frequency. Well, remember this formula? Speed is equal to wavelength times frequency. Okay. If the frequency stays the same, but the speed has to slow down, then to balance this equation, what would wavelength also have to do? Also slow down, or also decrease, right? Isn't that true? Do you guys see how the distance between these wave fronts decreases from the air to the water? Huh. Okay. And the only way for that, what that results in is that this ray that runs perpendicular to those wave fronts, has to bend, has to refract. You see that? Okay. So the fact that light moves at different speeds through different materials, that causes refraction. Okay. Now, yeah, see, I think what I want to tell you guys in the next few minutes here. Okay. But there was here, side story. There was one year I taught a forensic science class, and a lot of fun physics applications in forensic science. One of them that I liked a lot with this was, suppose there's been like some I don't know, some crime somewhere that's like shards of glass that are recovered from the scene. Well, glass has an index of refraction, but maybe it's like different, slightly different values for like different manufacturers of glass. And let's say, what car did it come from, or what manufacturer, right? So you have like some of those shardy glass. What you can do is put it in some materials, like some oil or some water, and like change the temperature of that. I want to say some kind of oil, where eventually refraction does not happen between that little glass shard and the surrounding oil. And at that exact point where there's no refraction, it looks completely invisible. You know that the indices of refraction exactly match. And so that's how you can determine the index of refraction of some little tiny shard of glass, something like that. So yeah, but there's laboratory ways to do that. But back to what's an equation that could tie all this together? I mean, that's really a nice picture, but what's an equation? The equation that's going to lead to this is called Snell's law. So do you guys see this vertical dashed line right here? That runs perpendicular to this the surface. Yeah, perpendicular line. And so the angles that we're going to measure are going to be with respect to that perpendicular line, just like we did for law of reflection, but now we've got refraction. So I care about this angle, I'll call this the incident angle, and this angle I'll call the angle of refraction. You guys that? And what Snell's law tells you, so Snell's law says that the okay, well, draw a picture real fast. Let's say you have like an air versus water, or like two materials, okay? Material one, material two. Okay? That for sure. perpendicular line, here's the ray, here's theta, I'll call it theta incident and theta refracted. Okay? It says that the index of refraction of air, so call it 1 or air post material 1, this is like material 2, okay? Multiplied by the sine of the angle of incidence is equal to index of refraction of the water in this case, or material 2, times the sine of the angle of refraction. Okay, that's called Snell's law. There's a geometry proof for this. You have to think really hard how to put it together, but that is Snell's law. Tells you how much something is going to refract. Okay? So we can do a quick demo right here. Say, yeah, we'll see that. Let's figure out what is the index of refraction of this material. And I think it should be, again, about 1.4, 1.5, something like that. Okay, so let's see. So we can figure this out. So this way to do is need a reference line. I'll try and slice it through and see what path it takes. Right? What path it takes. Right? Now it's actually going to refract twice to get to here, right? Once through across the surface and once across the surface. So I have to keep track of that. It's a little tricky. Say. Okay. Right, so I see it's coming in sort of at this angle right here. It's this point. Looks like it refracts out like right about there. Okay, this is gonna be a real rough simulation, but we're gonna make this work. Ooh, maybe I should switch to pink. Okay, so here's my laser light. Zoom. And then it had to have gone something about like that. Zoom. And then about something like that, it refracted out. Zoom, something like that. Okay. Now remember the whole perpendicular line that we're measuring with respect to. So do my best to get a perpendicular line to that surface. Be about right there, something like that, right? Okay. So I'm going to call this angle of incidence and angle of refraction. Okay. Okay. And then set up Snell's law. Okay. Well, let me see what those angles are. Oh, got a protractor. How handy. Now I do have to here, look around this way. Okay. So pink line crosses through. Looks like 48 degrees, maybe about 48 degrees. Okay. And how about the refracted angle? And here's where I have to extrapolate. So this is gonna go that way. See what that crosses through. I'm looking at about, oh, that's like 30 degrees. So 30 degrees. Okay. So 48 degrees versus 30 degrees. Okay. Now back to Snell's law. How's that going to feed in? So on the side of air, index of refraction is really close to 1. So I'll just call it 1. It's like 1.00 something. Times sine of about 48 degrees is equal to index of refraction of the glass, which can't tell you how much light would slow down in there. Material property times sine of 30 degrees. Okay. I can divide down sine of 30 degrees. So what is sine 48 over sine 30? And get index of refraction of that glass is, 1.486. Remember I said it was about 1.4, 1.5? What do you do? 1.49. There you go. Index of refraction. Now, here, run it. It's going to give guys something abstract, but I'll just do one better. Just got a demo to show you guys an interesting consequence of this. Snell's law. All right. Let's say this bunch. He has an even better prism. He's got this semicircle. Okay. So, okay, you guys see he's got a shallow incident angle relative to this normal line. He even labeled it normal for perpendicular to the surface. Okay. What's really nice about this shape prism he has, the semicircle, is that it doesn't do a double refraction. There's one refraction across the flat surface, but then since he's aiming it right at the center of what would be a circle, it doesn't actually bend through this other the curved surface because it's always going perpendicular to it. Okay? So see, he's making that angle of incidence bigger, 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 and the angle of refraction is also getting bigger, but not as great a rate. You guys see that? Okay, so zoom in towards the end of this. The fact that they expand at different rates, he can only go up to like 90 degrees for his angle of incidence, right? Right now it's at what's that, 70 degrees, but he can only go up to 90. But that refracted angle, well, it's sort of like approaching some limit. Like I said, the limit it's approaching is called the critical angle. Okay? So suppose you were like an ant crawling around the paper. Let's say you're on like this side right here, like at this 20-degree mark. Is there any angle you could ever shine this light so that you could see it at the 20-degree mark? It's never going to happen, right? So there's some critical angle. And also towards the end of this video, do you see how there's some reflection going on? See, if I zoom back to the beginning, I don't really see any reflection, but right there, I see some faint reflection. They get stronger, stronger, stronger. And at some point, it's all reflection, and there's like very faint refraction, but it looks like it gets cut off at about 40 degrees, thereabouts, right? It's about 40 degrees. If you did this from the other side, it'd be called total internal reflection. You got one lined up right here. Total internal reflection. Take a quick look at this. Yeah, right there. Right, so same thing, just opposite side. See how it just reflects. Okay. So suppose you're like a fish swimming around the water and there's a boat above you. If you're pretty close to the surface, kind of near the boat, like there's a place you can permanently hide from like any fishers that are like trying to find you. That's like that. I guess first world fish problems. And then put these ideas together. You could rainbow. I think it's a good thing to leave on. So rainbow is a consequence of both reflection and refraction. So if you have a bunch of water droplets, rainbows are always at 42 degrees from the viewer's point of view, and the sun is always behind you whenever you're seeing a rainbow. And of course, you're only seeing like the top half of what would be a complete circle, but the other half would just go underneath the ground. Especially like in a plane, you see a rainbow, then you'll see like a full circle, which is always at a 42-degree angle from your point of view. All right, see some more of those later. You guys have a good Wednesday.